with our next session. So welcome once again to all the participants. The second session will be delivered by Dr. Svetlana Brizev ma'am, and it will be based on the planning of confined machinery buildings for earthquake resistance and force transfer. So I expect all the participants to pay their kind attention. And if any questions they are having, they will be given ample time and opportunity at the end of this session. So they can put their questions in the chat box or they can ask the question by switching on their mics. So over to you, ma'am, to begin with the session.
Thank you very much, Aditya. So I will, maybe before I start with this session, I would like to show you, if it is possible, let us see if it works, those two videos that I wanted to show about performance. And I think it's convincing, very convincing and important always to show these videos about performance of shake table tests um, uh, of this stone masonry building. So were you able to hear, to see the video? Hello?
Madam, we can see the video, but the audio is not there.
Audio is okay. That's okay. You don't need
And
video, audio.
one more thing, madam, on the screen, you can see one stream. So you can press the hide button so that it is not visible on the screen.
Mhm. Sorry, I was if I was not just stop sharing. So I wanted to just to show this. This was in the context of on the topic of nominally reinforced masonry. I was concerned to exit from the PowerPoint presentation, so I wanted to share. I can repeat this if you want to for some reason to record it in some other way. But I would now like to proceed with the next presentation. So I'll
And
just
ma'am,
yeah.
if you can share this video on WhatsApp, my WhatsApp group, I will share with the participant.
I will. Those are two videos, both.
Yes.
And in fact, I can also, I have a paper that describes this testing, which is also good by that group
Okay.
from Peshawar. It's worthwhile looking at it. So it just shows the convincing performance. Please note that the reinforced masonry technology had also vertical elements with 4 bars, which are same as actually confined masonry. So it is in a sense confined stone masonry if you look at it, and really good performance. The tests were done around 2010. So I will share both the videos and the paper that describes the testing with all the details of the accelerations and all that. So right now I will proceed with the next lecture, and I will just share the lecture. So the topic of the lecture is planning. Another, step in introducing confined masonry is looking at the buildings as a whole. What do we need to take care of in planning the buildings for earthquake resistance? And before we move on to smaller details, to details of, of course, approach for simplified and then more complex modeling analysis, and then of course design, which will come at the end. So we are going from the broader topics to the more narrow topics in this course. So the topic, the first topic is planning of confined masonry buildings, and then a few slides on load transfer, just to confirm the way it works with the masonry or with confined masonry. So for planning, this is the most slides are related to planning in this lecture. The lecture will be around 45 minutes or maybe up to 1 hour. So key aspects are building configuration, wall layout, confining elements, and openings in confined masonry walls. I touched on some of these topics in the previous lecture, but there will be now more information. And I would say that at this point that again, all illustrations here are from the confined masonry book that I co-authored with Professor K. Mitra, and which you have as a resource. It is chapter 6. It is mentioned at the end. There are a few rules regarding building configuration, and they're not specific to masonry. And we numbered these rules and labeled them. So rule BC, building configuration 1, plan should be regular whenever possible. So if it is possible, it would be good to have a regular plan like shown on the left-hand slide, as opposed to this U-shaped plan, which is common in India, actually, in many buildings, where we have so-called re-entrant corners, which are circled here and are a source of additional increased stresses and forces and damage in earthquakes. So we should aim at having regular planned buildings, or then we'll give some alternatives if that is not possible. So what is acceptable irregularity in buildings? And this is also recommended by some codes. Acceptable offsets or irregularities, let's say up to 15% of the length of the dimension in which we are considering. And that is shown on these diagrams, that what is possible to do, like some maybe unrealistic, like the one on the right, maybe very small room or something. But anyways, it is what we would say, that if we have irregularity, that we set a limit to irregularity if possible. Or alternatively, of course, these are very small buildings, but this is a conceptual. These are conceptual diagrams. It is possible and feasible if it is a larger, if we have larger blocks, let's say schools, we can create a separate seismic gap between the blocks. So we get regular rectangular blocks which behave as separate buildings, separate structures in an earthquake. So it's always possible to create these gaps. Of course, it comes at the cost, because we need to have a double system on each side of the block. Like we need to have a wall, separate wall on each side of the block to complete one of the each building. So if that is, and of course there will be some openings, because these are still combined buildings, but for the purpose of seismic design, they will be considered as separate structures. For example, at IIT Gandhinagar campus, which I will be talking about, we will be talking about in the following days as a case study of confined masonry, application of confined masonry in India. This is an example of a student hostel, and you can see all these different colored blocks are all separate. Even though it's one structure, it looks like it is one building, but they have different wings, are separate structures, and there are gaps at these locations which are shown here. And interestingly, the building at the left right corner is the staircase block. This was designed as a RC frame, reinforced concrete frame. So most of the building is confined masonry except for this. We'll be talking about that, and Mr. Anal Shah will talk also about it as a designer, structural engineer, who designed these structures on IIT Gandhinagar campus. The other rule, which is not related to confined masonry, but is general when it comes to planning of buildings, is length to width ratio of a building, of individual block of building or a building, is that the ratio should not be more than 4. That is a general rule, and that is because in very long buildings, there are maybe some effects of vibrations which are unfavorable because of the length. It is also true that in a long buildings, there could be a more significant out of plane seismic effects. So it's always good to have what is shown here with the checkpoint, a green checkpoint, is to have something like more regular and not too elongated plan shape as shown here. So these are all, as I said, figures from the seismic, the confined masonry book. It is figure 6.6, so you can see even figure numbers. So you will read, I hope, chapter 6, and you will get familiar. There is accompanying text there. So adjacent buildings may be in configuration. If the buildings have, the blocks have different height, they must be separated by seismic gap. It is recommended anyway. So the gap, the size of the gap is prescribed usually by the codes. And so that the displacements, if the two buildings are vibrating out of phase, that there is no pounding or collision between the blocks. So this is a little bit exaggerated on the right-hand side, but should be a sufficient size of the gap in that case. So pounding is very common in earthquake situations. This is example of pounding. Pounding can happen if there have buildings of different heights, and or if you have buildings of similar heights, but as in diagram B, but the floor levels are different levels. So if the buildings are adjacent and if there is no sufficient gap, at least the floor should be at the same level, which means the floor heights need to be the same. What is very important for wall structures is that there is continuity of walls from the ground to the roof. So the drawing on the left is not acceptable. The drawing on the right is a must. We need to have we must have continuous walls. Walls cannot be offset in a masonry building. Perhaps this kind of situation may be acceptable in concrete frame structures, even though I think it wouldn't be acceptable in frame structures either. But in wall structures, the walls are the key elements and they have to be continuous. Maybe in case of partition walls, they could be offset, but load-bearing walls have to be continuous. And here is an interesting point, which I think is particularly interesting since India is at the beginning of the application of confined masonry. You know the buildings with open ground floors. In fact, there are many of them in Ahmedabad at least, and everywhere in India, in all cities, because they're parkades, at least in all times. That is how it was done. Nowadays, of course, more and more buildings have underground levels, and that is good. But if the building does not have underground level, then in many cases, ground floor is open in reinforced concrete frame buildings, and that was used for parkade. And we know very well that these buildings performed poorly in the 2001 Bhuj earthquake. In fact, a number of buildings in Ahmedabad collapsed of that type. And still there are many buildings are being built with that feature. So in confined masonry, a big no is to have an open ground floor. And in that case, we would need to have a reinforced concrete frame system at the ground floor, because that wouldn't be any more confined masonry system at the ground floor, and then have confined masonry building on in the upper floors. So this is so-called hybrid system, and it is not permitted in confined masonry, and it is not permitted by the code. So confined masonry can be done only if there is a continuous system, continuous walls from the ground to the top. This poor performance or collapse of buildings with hybrid system with confined masonry has been documented in China after the 2008 Wenchuan earthquake. In fact, there is a paper in the book, the paper has been referenced, which clearly shows performance of these buildings. And also I visited Albania after the 2019 earthquake there, and they had exactly the same system with open ground floor. You can see here they didn't open it. It is open, it is just light doors, but it is actually basically open at the ground floor. In Albania, it was magnitude 6.4 earthquake in coastal area of Albania in November 2018. I went there, so this is a photograph of a building in that coastal area of Albania, and open ground floor. And you can see a collapse of another building, so it is complete soft story collapse and the building had confined walls on the top, but the ground floor was not designed for the forces that are coming from this open ground floor. It was very poorly reinforced, obviously, and poor quality of concrete. But in any case, it is an example of a collapse of this hybrid system in Albania. And as I said, it's also very, very well documented in the papers from China after the 2008 earthquake. So confined masonry buildings in China performed very well, except for the buildings which had this hybrid system. So it's very important not to think about it at all as an option for confined masonry buildings in India, and it is not permitted. A very important aspect in masonry building is wall layout. See, this is now specific for all wall structures. It could be a reinforced concrete wall structure or masonry wall structure, but it is about walls. So obviously, ideal situation is the left drawing, symmetrical wall layout, where we have all walls symmetrical with regards to this vertical axis, in this case Y axis, that we have a centrally located wall or whatever, and then end walls. And or if it is not possible, then we have a very small eccentricity up to 10% of the length of the dimension in which we are considering. But if we have more than 10%, or this is just a reference number, obviously, but let's call it small eccentricity. Then if you have large eccentricity, then what happens is that we have a CR, which is center of rigidity, which is different from the center of mass, because in the building that has a symmetrical plan, center of mass, which is the geometric center of the building plan, coincides with the center of rigidity, CR. If there is any offset, center of rigidity moves away towards the location where there is a concentration of this stiffness or rigidity of the walls, and it moves to the left in this case, because these walls are longer on the left side. And in case of the right-hand side diagram, it also moves to the left even more. So there is a large eccentricity between center of rigidity and center of mass, which causes torsional effects. Of course, torsional effects can be considered and can be controlled by design. Increased forces due to torsional displacements due to torsional effects can be controlled, but it is not favorable. It's not desirable, but it is necessary in some situations. And as I said, these are some recommendations, but of course, in real design, it's not always possible to follow them. Another important aspect for all masonry buildings, including confined masonry, is that a minimum 2 parallel lines of walls are necessary in each direction. This is usually a part of the codes. So we cannot have less than 2 walls which are load bearing, and in this case, which are confined. That is the minimum, even in smaller buildings. Let's say we have a building with 4 walls. That means we have 2 walls in one direction and 2 walls in the other direction. So this is that box type structure. So, and then also the distance, if you have just 2 walls, the distance of these walls should be as far apart as possible, should be at least 2/3 or more of the length, overall length of the building. And that is shown for on this diagram. So it's shown in different directions, but it is the same message. And finally, sum of lengths, if we have separate walls, like it is shown here, W2 and W3, sum of lengths of these walls have to be greater than the length of the side of the building L. So if they have 1 wall, the length should be greater than half of that length. If you have 2 walls, then when we add their lengths, they should be larger. So in other words, most of the line has to be covered by the walls. It must be supported by the wall. And this is the same is shown for both directions. So these diagrams are exactly identical, except that they show walls in vertical and horizontal direction, the way it is shown on this plan. Okay. So now we are talking about confining elements, and in the code, we will show that these are some recommendations from the masonry guide, not from the code, but I believe the code, the IS code, would have similar dimensions. And I will, when giving an overview of the code, I will show you where this part is, so you don't need to memorize, you can check. Here are some rules for tie columns. So obviously we have, let's say in the confined masonry wall, we have 2 tie columns and a tie beam. And I consider this tie beam as a tie beam at the floor level. Additional band is not considered as a tie beam. It is just a band, which is a provision, but tie beam is at a floor level or roof level. So tie column dimensions are as prescribed by ERI guide and I believe by Indian code, is that the length is at least 150 millimeters and the other dimension is 110, which means that if this is 110, that means that it will be possible to construct half a brick thick wall. But from the practical point of view, this is next to impossible because we need 4 bars and it will be very difficult to construct 4 bars at such a small size. That's why I said that most applications I would expect to have 230 by 230 millimeter size tie columns. As far as tie beams are concerned, the dimension is also actually, I think this is a typo because the dimension of the tie beam, the slab is normally at least 100 millimeters deep, thick. So the overall depth of tie beam should be more than 150 if the slab is 100, but it has to be deeper than the slab. So tie beams are usually going to be integrated with the slab. As we have already in reinforced concrete floor systems, we do have beams at the edge. So that beam at the edge would serve the purpose of tie beam. It is not a separate beam. It is only that, as we will see in the confined masonry, the tie beam would only work for tension and compression. It would not act, it would not have any bending, any shear, so it would only act in tension and compression. So that is the only difference. Otherwise, it looks the same as the beam that would be anyways a part of the floor system, which is nice. Tie column is extra, obviously. It would not be a part of RC floor system. It is a vertical element anyways, but that is it. So in order to, this is very important, in order to consider a wall as a confined wall, let's say this wall ABCD is confined, wall BEFD may not be confined. You can see a door and maybe a large window. And unless there is additional confinement, we would not consider this wall as confined. So this would be considered unconfined. So you can say, okay, well, but we need to have doors and windows, and sometimes we will not be able to confine. That is okay, but for the seismic purposes, seismic design purposes, we would consider only walls that are fully confined, that are to be resist seismic forces. It is true that even though we don't consider this wall, it will take a part, it will resist a part of seismic forces, but we simply don't consider it. That is how it is. And that is also another very important rule. So in planning of, for example, IIT Gandhinagar campus, not every wall in the building that I've shown and the other buildings were considered as confined. They are part of confined masonry buildings, but walls were not treated as confined masonry walls. So these are now the rules that are included in that chapter 6 and also, as I said, in the code, and they are now numbered. So this is more specific than what is shown in the previous lecture. So first rule is that tie columns need to be provided at wall ends, at the ends of the walls. So here is, and the other is that tie columns have to be provided at the openings. That is number 5. Number 2, tie columns at the wall corners. And then there is a number 4, tie column at free end of the wall. And then also number 6, tie columns in long walls. If you have a long wall without any cross walls or transverse walls, we need to provide the tie column to, this is intended for out of plane resistance, seismic resistance. There is no other reason for that. And the wall intersections, wall corners, so wall corners, wall intersections. And you can see here, for example, that if you have a very short wall where length is greater than, less than height over 2, we may not provide the tie column, but then that portion of the wall is not considered as confined. That is on the right-hand side in the and you can see the box, no tie column at the end of the short wall. So this is anyways figure 615 from that publication. So openings are really important, ends of the wall. So anything, so both sides of the wall have to be confined. This is an example, and this was examples from the IIT Gandhinagar campus construction, that if we have an opening in the wall, let's say, then we don't need to have a confinement, this diagram B, confinement at the end of that cross wall. You can see on the left wall, because there is a solid wall, there is a confinement at the wall intersections. Here, in this case, when we have an opening, we can have a first confinement, first tie column at the end of the opening. There is no need to have an extra. We had a discussion at during the planning of IIT Gandhinagar IIT GIAN campus. So unless this wall, vertical wall, is very long, in which case there would be a need for extra tie column. So that is an interesting rule. And we talked about continuous tie beams at each floor level. As I said, you can consider these tie beams as parts of a floor system, as a floor structure. And in India, it is required to have a lintel band when the floor height is more than 2.5 meters, and it is in most cases, practically all cases. So I would expect that all confined masonry buildings in India will have RC lintel band in addition to this beam. So this would be an extra expenditure in confined masonry, which is not there in other countries, but it is simply based on Indian practice to date on reinforcing masonry. Here are the examples of how confining walls can be, how confinement can be provided at the openings. You can see on the left diagram A, both sides of the openings are confined. Therefore, both walls on left and right side of the opening are considered as confined walls. On the right hand, on the middle B, only one side of the opening is confined. Therefore, you can see the confined wall is only on the right side, where the wall on the left side is not confined. So we will consider a right wall in the seismic force calculations. And then the third, the diagram C, shows a wall which is confined only at the ends, but it is not confined at the openings. And also the size, the distance between the end of the wall and the opening is less than height over 2. Height is the wall height at the floor level. Therefore, this wall is unconfined. So this wall would be disregarded or not considered in the seismic force calculations, seismic distribution. So it would not be assigned any forces for seismic. It, of course, it is there. It would carry gravity loads, and it would also resist some seismic loads, but it would not be designed for seismic loads. So it is maybe also a margin of safety to disregard some of these walls, even though they will take some loading. If you have small openings, such as ventilators, what is important in the planning is to put them outside the diagonals. You can see the diagonals on the left-hand side. And in that case, we consider this wall as solid. And these are openings which are less than 10% of the wall area. And if it is on the diagonals, like in the diagram B, then we can put a confinement. And in that case, the part that is solid without openings will be considered as confined wall, while the part on the right-hand side of the opening is not considered to be confined. So you can see confined wall, unconfined wall. So in this case of small openings, we don't need to model openings or include them. We will just consider this as a solid wall. That would be good for sufficiently good for design. Then openings aligned needs to be aligned. That is a rule about openings, have to be aligned up the building height. You can see the drawing on the left shows scattered openings which are offset with regards to from one floor to the other. In confined masonry, we need to have an opening which are aligned vertically so that we can place confining elements continuously up the building height. That is critical in planning of confined masonry building. So what happens if we have discontinuity in confinement? Let's say we have at the ground floor, we already discussed that it's not possible to have hybrid system, but we have some door openings at the ground floor, which we not have at the upper floors. So we will simply consider that panel with a door, we may consider it as unconfined, where the panel above it will be confined. So that is also possible in a numerical model. In the models for confined masonry. So we'll just disregard the ground floor panel, but we will consider all the other panels. And this drawing B shows that both panels are continuous and the same. But obviously, certainly there will be situations like the diagram A here, that there will be door openings. There must be several door openings at the ground floor and more openings, but as long as we have sufficient number of confined walls, which we'll learn how to check through calculations, then we are okay with these openings at the ground floor level. They're necessary. So summary of these planning rules. In the book, you will see the summary of planning rules for building configurations. Plan shape should be regular whenever it is possible. Length to width ratio should be less than 4. Adjacent buildings must be separated by an adequate seismic gap if there is different height. And confined masonry walls must be continuous up the building height. Regarding wall layout rules, wall layout should be as symmetrical as possible with regards to the center of the floor plan, centroid of the floor plan. Minimum 2 well-separated parallel lines of walls are necessary in each direction, and also sum of wall lengths for each line of walls will ideally be minimum 50% of the building plan dimension. Confining elements in confined masonry walls, C1, dimensions of key components of they're shown. Wall panels must be confined by reinforced concrete elements of all sides. Rule C3 is a rule about all locations of tie columns, which are shown, and these are summarized. They were shown on the plan drawing. Rule C4 is that the reinforced concrete tie beams must be provided on top of each wall at each floor level at maximum 3 meter spacing. When wall height between floors is greater than 2.5 meters, a continuous horizontal band shall be provided over the openings. And finally, a few rules regarding the openings. The tie columns, rule 1, tie columns should be placed at both sides of any opening with an area of more than 10% of the wall surface area for one confined masonry wall. Otherwise, the wall should not be considered as a confined wall. The second rule is for walls with small openings. If the opening is outside diagonal, it can be ignored. And when it is on the panel diagonal, an RC tie column must be provided at the opening. Otherwise, the wall is not confined. O3, openings should be placed in the same position in plan along the building height, and the tops of openings should be at the same height. That is what is shown. So that is all about this planning of confined masonry buildings. It is all explained in detail in chapter 6 of the book, which is also assigned reading for you in preparation for tomorrow's classes. So now the second topic, which will be just a few slides, but maybe more a discussion explanation, is load transfer or force transfer in confined masonry buildings. And I put masonry buildings because it is the same whether it is confined or any other form of masonry building. Masonry buildings are load-bearing wall structures. Load transfer is similar to frame structure somewhat, but there are some differences. There are two types of load transfer, gravity loads and lateral loads. For gravity loads, obviously, if you have a floors or roof above, there will be all the loads will be transferred to the walls. That's why they're called load-bearing walls. How do we calculate the loads on the walls, in the walls, due to these vertical loads? It is similar. This is a somewhat parallel comparison between between the wall system and frame system. Let's imagine that in this grid line AB there is a wall. So tributary area for the wall would be half of the length span on each side of the wall, between that wall and adjacent walls, whereas in the columns, and it would be equal to the wall length on the other side. Whereas if we have a reinforced concrete frame system, the tributary area would be like a square, rectangular shaped on all four sides around the column. So that is difference, but the concept is exactly the same. For the column, we take tributary area in one and the other direction, the same is as for the wall area, for the wall tributary area, but somehow the concept is exactly the same. That is the message. When it comes to lateral force transfer, or how lateral forces flow through a masonry building, first the loads are transferred to the horizontal elements, which are these diaphragms, which we talked at the roof and floor level in case of reinforced concrete slabs. And then these diaphragms act, and imagine that we have walls only at the ends of this building. So these end walls act as supports for these diaphragms, for this horizontal loading, and the reactions of this loading, which you can see on this diagram, are actually the forces that go onto the walls. So you can see now the forces that are being transferred at each floor level from the diaphragms to the walls. So in this simple case, there are only two walls at the ends of this building, but there could be many more walls. And through this course, we will go over the rules or the principles by which we can calculate forces in the walls through hand calculations and or of course numerical models using SAP 2000 software, for which I believe you got the license. So we have three steps here. Step number one is load are collected by the horizontal structure, by the diaphragms. The second is diaphragms transfer the load to the walls. And then third is we need to consider these loads due to lateral loading in the walls and design the walls for shear, bending, and then of course due to lateral loads, and then due to and also axial load or gravity load, that is which was discussed below. So this design of confined masonry walls for axial load, bending, and shear will be is scheduled for Thursday, I believe so. So in any case, all these topics will be covered. It is important to understand the big picture, how this works, but then we will go in details over each of these topics. Planning, the topic of planning of the building is very important both for engineers and architects. In some cases, the architects may not be educated, but they may not have, as we learned, there are challenges in the curriculum of engineering and architectural programs, that they may not have any education for related to seismic planning. Planning is high seismic zones, but that's why you engineering students, future engineers, and or engineering practicing engineers, engineering professors are there to educate them. In this book, chapter 6 is dedicated to the planning, and you will need to go over it. All the illustrations are given from this lecture are in chapter 6 of the book. And that is all for this lecture, which was related to planning. Do you have any questions? Stop sharing. Okay, so yeah, so this was the lecture on the planning and the force transfer in the masonry, confined masonry and masonry buildings, I would say so. Any questions? I'm not sure, Chaitanya, if you shared already the presentation, the book with the students. That is really important because they would need it for really preparing for the future classes.
Yes, sure. Yes.
Book has been shared. So I will go over the book a little bit before, maybe in the meantime you can prepare your questions if you and give a little bit of history about it as well. So so as I mentioned, the first confined masonry publication, larger publication, or it was called monograph, was developed in 2007. I wrote it. I was in India as a part of the NPEEE program, which was convener was Professor Sudhir Jain at IIT Kanpur, and I spent some time, about 3 weeks at IIT Kanpur, and I was requested by Professor Jain and Murthy and Rai to write a publication on confined masonry because at that time there was no experience on confined masonry in India. And I wrote the first version of that book, which is available in electronic form on the NICE's website and was published by NICE in printed form too. Since 2007, it was translated in several languages, Hindi and I believe some others. So anyways, in 2019, another version, and it was reprinted with some changes, so it was called second edition. So in 2018, I co-authored another version of it, which is more comprehensive, with Professor K. Mitra, which is a professor of architecture in Kolkata, and we have been collaborating for years. And the publication was published by NICE, but with funding from BMTPC and IIT Gandhinagar at that time. On the cover page, it was lots of information in the publication or graphics, Indian graphics are from the construction of IIT Gandhinagar campus, such as this is a housing at IIT Gandhinagar campus. These are also construction of confined masonry buildings. So as far as this publication is concerned, it has around 150 pages. And the content is, I will just go over the table of contents to illustrate, to introduce the publication to you. So first chapter is general on earthquakes and how they affect buildings, how earthquake forces develop. So it is basic introduction to earthquake engineering. That's only first 10 pages or so. Then the second chapter is about confined masonry, key components and worldwide applications. You will be able to see examples of confined masonry construction around the world. And the third chapter, which I also assigned to you to read, is how are confined masonry buildings different from unreinforced masonry, and how are they different from reinforced concrete frames with masonry infills. And then the fourth chapter is on how earthquake forces are resisted in confined masonry buildings. So we will talk about it as a part of seismic design, the topic of designing of confined masonry buildings. That will be later on this week. And we will also have a presentation on how confined masonry buildings performed in past earthquakes. It is chapter 5 in this publication, but I will show not necessarily only photographs from the publication. Obviously, I have my own photographs in addition to that. But all these chapters are really important to understand the behavior and performance of confined masonry buildings in past earthquakes. Chapter 6 is conceptual planning, architectural planning, and design of confined masonry building, and it is exactly what was covered in this lecture. So chapter 6, that's why I said it's an assigned reading. Preliminary seismic safety check for confined masonry buildings. It talks about so-called wall index approach, which is a simplified method for checking adequacy of or amount of confined masonry walls in the building. Tomorrow we will talk about that. We will have a lecture on simplified method for seismic design, and that is based on this wall index. So it's very useful because it gives us an insight into whether before we do detailed analysis, detailed check, design check, whether this is sufficient or not. Chapter 8 is also of interest. It is construction of confined masonry buildings, including building materials and construction practice. Tomorrow we'll talk about building materials or construction materials for masonry as one lecture, which is also important for further design. But it also goes back to understanding what is the minimum requirement of materials when it comes to confined masonry. In the introductory lecture, it was mentioned, a few introductory inauguration speakers mentioned that confined masonry is a forgiving practice. It does not require advanced skills, and that's why it may be more suitable for some applications than reinforced concrete frame construction. But some minimum requirements are there for any construction technology, including confined masonry, and some of the rules are and guidelines are provided here. And chapter 9 is concluding remarks. And Appendix A includes sample construction specification for confined masonry, which may be of interest to engineers because, as I said, specifications are not there. But CPWD in India has introduced specification at the time of the confined masonry of the IIT Gandhinagar construction, and this specification is based on CPWD specification. So in order for this technology to be practiced, specific construction specification is very correct, and appropriate construction specification is very, very important. So that is an overview of the publication. And I'm also wondering whether you shared whether you share the code with the participants, I understand, or the students in the course. I understand the code has been issued, but I shared with you also that code. So Chaitanya, have you shared it? If not, I would suggest to share it maybe among the materials for tomorrow's class.
Yes. Presentation, and it is shared on their WhatsApp group, and they can refer from that.
So they have also code as a part of the WhatsApp group.
Yes.
They have publication that I just presented, and the code as well.
Yes, sir.
Okay, that is good, because we will be going over the code and using the provisions of the code, so it's important to have. So my suggestion would be then to review this publication, as I said, chapters 1, 2, and 3, which we talked about today, and 6. And code, as I said, we will be making an extensive reference to the code throughout the design part of and analysis part of the course. So for the beginning, it's important to get familiar with confined masonry. That is the purpose of today's lectures. So that would be all. Mm-hmm.
Yes, I have shared a code of confined masonry as well as IS 1893 also. It is already available.
Excellent.
So 1893 is also required for the calculation. So it is also shared.
Exactly.
Yeah.
So these codes are available free of charge in India, isn't it? So they're
Yes.
available online. That's good.
Yes.
So anybody can download them anyways, even without this course.
Right.
Okay. And the confined masonry code is also available right now. At this moment, it is available online or not? On the BIS website? Not yet.
No, we haven't checked it, but
I think it has not been officially released, but it has the year 2022, so it will be released this year. I think it may not be still available, but for the participants of this course, we shared it because we have access to it.
Yes.
It may not be available yet, but it definitely will be released this year. It has the year 2022.
Yeah.
It's finalized. So the version that you have is final. The only discussion is being about the drawings, whether the size of the drawings and things like that. So text is final, and even the drawings are final. It's just the appearance of the drawings that maybe somewhat changed, but maybe not. We will see. So yeah. Thank you for this. And any questions about this? The lecture, as I said, many of these topics are general, but we included them because they're very important and they need to be followed in planning of confined masonry buildings. And as I said, it is more or less except for these rules about the openings and all that, general planning rules are exactly the same as for any building, and then specifically any masonry building. There is nothing special. We want to say that confined masonry is not too special. It is special, but not too special. It is special in terms of design, because design, as you will see, will be something new that has not been done before in India, because there was no need for it, because there was only unreinforced masonry. But in terms of the planning and many other aspects of seismic, I would say, analysis, it would be similar to what already, I believe, engineers would be familiar with from their background and training. So any questions?
Yeah.
One, Tanya.
Yes, ma'am. My question is yeah, you have shown one slide in which you are showing confined masonry building is on RC frame. Such kind of practice is going on in the other countries.
Yeah. In fact, I can share as a part of the additional material code in, not code, actually it was permitted by the code in China. So they practiced that in and performed that. It was devastating. These buildings collapsed in the earthquake in 2008. After the earthquake, there were papers which were published and by different authors in English, of course, and it is well documented. So this is shown that it is not permitted, and I believe in the Indian code there is one sentence which disables that that it is not possible to do it, not allowed. It will not be allowed to do that in India. So if you have a frame system, go ahead with the frame.
Yes.
If you have confined masonry, go ahead with confined masonry. As I mentioned, some openings obviously will be there at the ground floor, which will not be there at the upper floors. That is simply the nature of design, but not completely open for garage or for any other purposes. Then that cannot be called confined masonry. That is a hybrid system, which is very negative in terms of seismic performance.
Right. Yes, I think we have two raised hand, Yogesh Chavan and Poonam Modi. Yeah, Yogesh, you can go ahead.
Flat slab as a floor system for confined masonry?
Which floor system is used? Well, that is a good question. In the course and in most applications, floor system is rigid floors such as reinforced concrete slab, similarly to as what is current practice in India. And if you design G+3, G+4 building, normally system would be concrete, not timber, for example, at this time, isn't it? So we talk about that. So we talk about engineered confined masonry in this course. However, in some countries, like for example Indonesia, let's say if you have a single-story building or even two-story building, they may be using timber floors, maybe in some rural areas. But in that case, the recommendation is to provide a very robust tie beam at the floor level, which will enable this box type action, which I mentioned in the first lecture. But it is, I'm not sure if in the code, I'll check, we specifically requested to have a rigid system. So it could be a requirement of the code that always the floor system has to be rigid, which means, in other words, reinforced concrete floor system, at least for the roof. Of course, it could be a sloped roof with, again, in that case, it would be a tie beam, which would be more robust at that level. It does not have to be a flat. I know in India, due to climatic conditions, at least in the part where Gujarat is flat roofs. So that is again reinforced concrete slab. But let's say if you go up in the hilly areas of, let's say, Maharashtra or some other states, there may be a need to have sloped roof. In that case, it would be still possible to construct confined masonry, but with the robust tie beam at that level. So there will be RC beam, and then which would serve as a support for the roof structure. But that is a good question. Yeah, behavior could be okay in both cases, but I say most applications of confined masonry are with rigid systems.
Okay. Okay, ma'am. Professor Poonam Modi. Poonam, please, you can ask
Yeah.
a question.
Yes. Good afternoon, ma'am. Ma'am, my question is like, as far as the architectural features are concerned, what degree of freedom do we have to incorporate this architectural features in confined masonry buildings, such as arches or bay windows, or anything beyond that?
But see, thank you, Professor Modi, for that question. It's a very good question. I believe you will have the same type of freedom as for any other masonry structure. So let's consider this as a masonry structure. The only thing, as I said, and I try to emphasize that, I know maybe I'm repetitive, but maybe it's good to repeat sometimes when it is first mentioned, is that we need to take care that we have sufficient number of these confining elements. So you can always have some features which are not confined, but which are nice architectural features, and you want to have them in order to achieve that aesthetic aspect of the building. I think confined masonry should not confine this and restrict these features, but as long as it is within the frame of this, confining element which are present in sufficient amount and extent, I don't see a problem with having an arch within a wall, as long as it has confinement at the ends, and confinement is can be present even if it is arch. So that wall with an arch would be considered as non-confined, which is fine, as I mentioned. And tomorrow and over the course, we will go over the way how we can allow that, and how can we, as some policemen or police women, say, oh, this wall is confined, this is not confined, and how do we can make the building work even if we have those unconfined walls with large or unusual openings such as arches. It is perfectly fine. I don't think it would negatively affect the performance of a confined building, masonry building in an earthquake. And balconies also are okay. Let's say in IIT Gandhinagar campus, if you see, there are lots of balconies. Hostels, of course, they don't have balconies in students' rooms, but all these features are present in the campus itself. And so these are normal buildings, very nice buildings, in fact, if you look at the buildings that are on the campus.
Okay, thank you, ma'am.
Yeah, in fact, you wouldn't be able to say you're welcome if you look at these buildings now. You visit the campus, and I wish we were together and we could go there. You would not really be able to tell that these are confined masonry buildings. You would just see them as nice buildings, but you wouldn't be able to tell that they're confined masonry. That is
Absolutely,
maybe
ma'am,
good and
because we
bad.
have definitely visited. We have visited the campus. We have seen the buildings. They are definitely appealing, and yes, they really give a very good feeling, very comfy feeling. So
Mhm.
yes, I think this can be extended to our aesthetic features also. So we have
Yeah.
visited the campus.
Yes, and that is great. And you know what I think, and I believe you are maybe are you architect, Professor Modi? You're
No,
architectural
I
professor.
am. I'm teaching in this applied mechanics department
I know.
itself at ND
Okay,
College.
okay. Yeah. Okay, that's right. So I'm thinking that architectural professors could be leaders, or architects could be the leaders to come up with some examples when the confined masonry starts to be applied, of how all these features can be used, and take photographs, document them. I'm thinking that in the future, at the beginning, at the initial stage of application, this will be very important. Sorry, I ask you. I think we might have met. I thought because maybe there are maybe some professors from SEPT University now that they have architectural professors. So, anyways, yeah, that's a good idea for future. But I don't see any restrictions actually, any major restrictions at least. Anybody
Thank you.
else have?
Yeah, we have Dr. Manish Shah. Dr. Manish, you can go ahead with your question.
Madam, in your this second session, very second lecture, you have emphasized a lot on tie beams or lintel bands or tie columns. So indirectly, we are infusing RCC elements into our configuration. Is there any sort of research being done by your college or any other organization where we itself are considering or converting our masonry elements as in reinforcing elements instead of going for RCC element?
Well, I believe that global practice is that if you have a brick masonry, it's very difficult to reinforce it, as I mentioned in the first lecture. It's very painful, and you cannot provide that same amount of confinement at the ends with 4 bars if you have brick masonry. So it's simply impossible, unless you have a pilasters, which is a practice that is a thing of the past. So for that reason, these elements are, instead of having a masonry element, you have a concrete element. As I showed you in Mexico, I showed an example where they created, but they have a long, many decades of combined masonry practice. So their industry has gone so far that they have elements which are made of masonry, which are confined elements. And I shared that with you. In fact, if you look at my first presentation, so they have a whole industry that is tuned towards confined masonry, which is beautiful. And I'm sure that will happen in India with so many entrepreneurs and capable business people, particularly I would say in Gujarat. Maybe Gujarat will be at the forefront of that movement. So what I showed you for Mexico, you can see, which I hope will happen in India. See, they have these reinforcement cages are prefabricated. So you order 3 meter or 3.2 meter long cages for every floor, and then you may place some extra bars there, and you can see the masonry element, which is large enough to so that the cage can go into it. So it is masonry element, but it has to be hollow. It has to be large enough. And in the absence of such elements, the next best thing is to use reinforced concrete, which, as you know, we are easy to form and in any size and shape and all that. So in the absence of masonry elements, we use reinforced concrete. I can say in the world, mostly it would be just like what I explained. It would be with reinforced concrete cast in place. In Europe too, Eurocode also prescribes confined masonry. It's used in Europe. These are concrete elements, but innovations are possible. There is no reason why there could not be a masonry element just like this, where it could be done. But it cannot be done by bricks because it is very painful. I'm not sure if you witnessed any time construction of vertical reinforcement in brick masonry, but definitely 4 bars are impossible. And even in 1 bar, so much cutting is needed at each corner that I don't see how it would happen with so many required confining elements, because it's not, you're not talking about 4 elements. It's in larger buildings. It will be so time consuming for the masons and impractical to do that. That is simply reality of the, but innovations are possible. They would be really welcome in India. I'm sure that could be a very good business one day.
Thank you, madam. Thank you.
Yeah, you're welcome. Or, you know, or there is alternative of reinforced masonry. But what I'm saying is that except for a very few countries, quality of these hollow blocks are very poor, extremely poor, and they're next Adobe. You see, I had Adobe. Now next thing is hollow concrete blocks, because they are brittle. They have these thin shells outside. In Haiti, they killed those people. All people died due to these concrete blocks. It's horrible. You can drop them from the ground, from the height, and you drop them and it disintegrates. Strength is worse than Adobe. But people buy them, and they would, even if there is a plant-based production there, they would buy from the private small manufacturing because they were cheaper. So common man does not know what is good. They know what is the cost. They have their budget and they go by the budget.
Sure.
That is sad.
Sure. Thank you. Thank you.
So we have to be careful with the application of this hollow reinforced. And the second constraint with the reinforced masonry, which I would like to emphasize, and we have seen issues even in the lab. I've done lots of research in Canada. My only research is on this type of construction, because that's the only thing that is done, is grouting. Once it is grouted, there is no way you can see whether it is fully grouted or not, and whether the grout has gone throughout that height or not. There is no, only non-destructive testing can show. And during an earthquake, if it was not fully grouted, the reinforcement is usually very corroded. And I've seen that in Chile. After the earthquake, it corrodes after a few years, and practically there is no vertical reinforcement anymore, horizontal reinforcement. So that is, it's a the system that requires high level of supervision and good quality of masonry blocks. So that's why confined masonry is good. And I like the fact that there is a concrete elements at the end. And I've seen that at IIT Gandhinagar campus, because when you remove the formwork, you can see if something has gone wrong. And then it could be repaired if as needed.
Okay, sure. Thanks.
You're welcome.
Okay. Next question. I think Shashwat is there. Shashwat, you can ask.
Hello. Audible?
Yes, maybe a little bit louder, but you're audible.
Ma'am, I just want to check, like, what is the increase in cost for confined masonry as compared to unreinforced masonry?
I don't know. The answer is short. So more studies need to be done. Even if you look at the cost of bands, there are some stories that say that it is just a few percent, let's say 2%, 3%. Here it is more. So I would more compare confined masonry with reinforced concrete frame with infills than with unreinforced masonry, because confined masonry is to be used in seismic zones of India, where you need to use some form of reinforcement. So then if that is so, you would already need to use bands. So maybe let's go by saying additional cost of confined masonry over masonry with bands. We already have lintel band, which is the same. We have this tie beam, as I said, is a part of floor system anyways. So we can consider it as a given. So the only additional elements are these vertical tie columns. And as you know, in Indian code for masonry, reinforcing masonry, there is requirement for 1 bar. Here we have 4 bars, and we have a more robust element. It may not cost that much more than I would compare it to that, but not unreinforced masonry. Let's nominally reinforced masonry if you wish, because we are talking about applications for seismic zones anyways, where you would have to have, if you follow the codes, you will have to have these concrete elements, which are now called bands, and vertical bars at the corners. So there will be incremental higher cost, but there is a higher safety, because 1 bar is never going to be as effective as this tie column for sure. And we are talking about taller buildings. Ambition is to use that for apartment buildings, not only bungalows, like apartment buildings or this, let's say, institutional buildings, school buildings, or university buildings. Or apartment buildings, let's say G+3, G+4, that are wouldn't be used in unreinforced masonry anyways. So that's why it's not appropriate to consider. If you look at a single-story building and you are thinking of unreinforced masonry or confined masonry, I think the cost will be, difference in cost will be large, just because the size of the building is small. That's my opinion, without doing calculations. But I think more studies need to be done, but it is just a matter of safety, not a matter of cost. And it does not come to extensively higher cost compared to what is currently done. That is, let's put it that way. But you're absolutely right. These cost comparisons need to be done. So I hope there will be more student theses done on design unreinforced masonry versus confined masonry versus frame with infills, and that will tell us, and applications. Because at IIT Gandhinagar, we actually don't have a real cost comparison, because some buildings were either done in infill or in confined masonry. So there was no identical design done in both systems. So there were some general cost comparisons done, but I don't think in India currently we have specific cost comparisons done for this, and they're needed. That is a very good point, because cost is always an issue, no doubt about it.
Okay, ma'am. Thank you, ma'am.
You're welcome.
Yeah. Now next is Professor Deepa Raval. Want to ask question? Yes, ma'am.
May I?
Yes, yes.
Yes, please.
Ma'am, is there any effect of bonding of the confinement element is observed, like the type of bonding which we use in bricks? Does it have any role play to the confinement effect? Or
So you mean whether it is English bond, Flemish bond, and things like that, bond type of in masonry?
sometimes we go for lock and key keying of the element. Does it
Yeah, it will affect the strength of masonry. So whatever affects the strength of masonry affects the strength of confined masonry. So if the locking improves strength of masonry for compression and shear, what I'm saying is compression strength is critical because compression strength is the governing factor for all other strengths. So I'm looking at it that way. So locking would improve bond and it would improve, of course, interaction between masonry units. But the main point is compression strength, and compression strength strongly depends on the compression strength of bricks. So how strong are the bricks or blocks, whatever is used. So I think it's the same if we set that the minimum strength, let's say for this system is, let's say 5 megapascals or whatever in the strength units. How do you achieve these 5 megapascals? It's up to you. In some cases, you are going to have better, stronger bricks. In other cases, you will have a special system. So it is, I would say these are alternatives. You can achieve the strength in several different ways. But in terms of bond, horizontal bond between mortar, that was another question, mortar and the bricks, I don't think there is a special requirement when it comes to confined masonry. It is the same as for any other masonry. And as you know, in India, bricks are made with the frogs and all that. That is a good thing, but it is not necessary in many other countries. I mean, frogs are definitely good practice. In Canada, for example, bricks are made with holes. So we have hollow bricks with 3 holes, and these holes are acting as frogs. So any kind of system that improves bond is good, but compression strength is the key by which we define whether masonry is adequate or not for confined masonry, as we will discuss tomorrow, actually, already in the materials section and further on.
Thank you.
Okay.
You're welcome. Good question.
Yeah. Any more question, please? Any more question, please, from the participants? If there are no questions, then over to Aditya. Aditya?
Yes, sir. Yes, sir. I guess there are no questions from the participants. So once again, thank you so much, ma'am. It was quite an comprehensive presentation and an elaborate description for all the concepts, as well as an apt answer for the questions asked by the participants. I hope the participants were satisfied with all the answers and the presentation, and they will be eager to join for our upcoming sessions also. Thank you, ma'am.
Thank you very much, and thank you to all for attending. See you tomorrow, I mean, for my lectures, and in the continuation, are you announcing, Chaitanya, for the lectures in the afternoon or after lunch? I guess it's lunch break
yes.
now.
Yes, yes.
Yes, yes.
Now there's a lunch break, yeah.
Yes, ma'am. So there will be a lunch break for all the participants and the members. Upcoming session will be delivered by Major Dr. C.S. Sangvi sir, who will be discussing in detail on the topic of earthquake basics, concepts of earthquake resistant design and challenges in India and design assignment. So when can we meet, sir, now? How long the break?
I think 2 o'clock is fine. It is almost 40 minutes from now.
Right, sir. Right, sir. Absolutely.
Yeah. So I think 2 o'clock, and we will share a different link in the WhatsApp group. So participants are requested to join by the new link, right?
Done, sir. Done, sir. All the participants are once again requested to join by the new link, which will be shared on the WhatsApp group by 2 p.m. By that they can have their break and lunch. So we are ending this session over here for now.